Hey, my name is Max. I'm going to talk about some of our general design decisions with our robot. So we decided to go with a long configuration for our drive base, for maneuverability and turning scrub, and for the fact that we didn't actually want to pull the cube inside of our frame perimeter. We also wanted to have a lift that was dual purpose as both a cube scoring mechanism in both the switch and the scale, and also our climber. And then in addition to having a climber, we wanted to be able to deploy extra hanging bar for our allies to climb. And as you may see on our robot, we have a lot of custom machined parts. This, however, isn't necessary. We just did this because we had access to these machines. If you don't have those resources, you can change things up and do some different manufacturing techniques. So for the drivetrain, for example, using these clamping gearboxes, all you have to do is drill a through hole for the shaft to pivot in, and you can do this with a hand drill and a hole saw if needed. Also, some of the other parts, like this plate on our intake, this can be done by printing out your CAD model one-to-one on a piece of paper, gluing it on, punching all of your holes, and then just drilling through those with a hand drill, and that will get you close enough results for most FRC applications. Another thing that we did is we used a fair amount of welding to assemble our robot. This was mostly in the interest of time, only having 3 days. However, if you don't have access to welding, you can assemble your robot with either rivets or bolts through a variety of off-the-shelf gussets that are available for FRC teams.
Hi, my name is Mitch Gaines. I'm part of the Robot in 3 Days team here at WPI. I'm going to talk to you a little bit about our drivetrain real quick. So we have a 6-wheel West Coast drive with 4 stems. We figured that the 4 stems would be enough to get us around the field quickly and enough to play defense if we needed to. Additionally, it gave us enough torque to get up the ramp. Another consideration that we had was the size of wheels that we use. So we use 6-inch wheels because we found that using 4-inch wheels caused us to bottom out when we were going up the ramp to hang. So those were a few of our considerations. Additionally, all the parts that we used for it were found on the shelf, so we didn't have to order any parts for this.
Hello everybody. I'm going to be talking a little bit about our intake mechanism and the decision process behind why we decided to go with a wheeled intake over some other methods, and also how we built it and how it works. So the initial process when designing this, we were looking at a grabbing mechanism that would be able to pick up the power cubes versus something similar to what we have as a wheeled intake. And we ended up going with the wheeled intake because it had the form factor we were looking for, and was also able to pick up the power cubes in any orientation, which was, in our opinion, the most effective and most strategic way of being able to handle the power cubes. So the actual intake mechanism has 2 arms on either side of it, and both of these have a motor each that drive 4 wheels in total. These wheels are offset from each other, so the ones in the front are slightly further out than the ones in the middle, and this allows us to be able to grab the cube in slightly different orientations and have it orient itself in the correct location as it moves into the actual feeder mechanism. The cubes are just being held up with the innermost wheels. The point at which they grab onto the cube fits into some of the natural pockets within the crate on the underside of the actual structure. The arms then are tensioned into the center of the intake mechanism using surgical tubing, and this again allows us to help funnel in the cube when it is in different orientations or different angles. So the last part of the intake mechanism is its ability to fold up and down. The intake mechanism is able to completely fold itself up into the robot. The The decision process behind doing this was to allow us to be able to start in the starting configuration, but also have the intake mechanism come outside of the robot. We were deciding whether or not we wanted to have it potentially be a U-frame robot and have the power cubes go into the robot, or have our intake mechanism outside of the robot. And to us, we decided that having it outside the robot would be the most effective in being able to kind of maneuver the cubes and be able to pick up the cubes, as well as the delivery of the cubes into the switch and the scale. So we opted to allow our mechanism to fold into the robot and then be able to deploy outside of it. And so this is done using the versaplanetary gearboxes with the single stage reduction gearboxes. Unfortunately, due to the lack of resources that we have, just we're running out of all the parts and stuff, these are not as strong as we would like them. So if we were doing this for real, we would have a lot beefier gearboxes, but they worked for what we are doing now, which is allowing it to hold itself out. But the mechanism itself just allows the intake to come out so we can feed it, drop it, and then fold back in when we are climbing and starting the robot starting in the robot configuration at the beginning of the match. And that allows us to have a successful robot.
Hi, my name is Cam, and I'm going to talk to you a little bit about our lift. There are two kind of lifting challenges in this year's game: lifting power cubes and lifting the robot at the end of the match. We wanted our lift to be able to achieve both tasks. We considered an arm, a 4-bar linkage, and a telescoping lift. We decided not to go with an arm because given how high we wanted to lift the cube, which was 6 feet, to be able to get it into the scale, it would require a long lever arm, which would mean a lot of torque at the shaft. And that's not really desirable for hanging. We didn't want to have to design a transmission like that in only 3 days. So we decided to go with the telescoping lift. We were sponsored by Rev Robotics, and they provided us with their new Rev lift kit. And I gotta say, we really like it. The V-groove bearings, what they ride on is off-center, eccentric, which enables you to tighten them really well along the extrusion. We really like how well they slide. Here we have a 2-stage telescoping lift. It's driven by a drum which is built into the chassis, and that drum is driven by two 770D5 Pros through 63-to-1 versaplanetary transmissions. There are 3 cables in this assembly. So there's one cable on one side, one cable on the other side. Both of them are for lifting. So when the lift raises, the drum is reeling in cable. And the third string is for climbing. So it's attached to the gripper, to the drum. So and it's wound in the opposite direction. So while the lift is going up, the third cable is actually letting out line. In order to take up some slack, we added a spring in parallel, right here. And that's so that our line didn't get caught in our gears. So this third line is necessary so that we can also use this mechanism to climb. So at the end of the match, we'll lift the whole assembly up, and then we'll drive the drum in the opposite direction. We'll pull on the cable, and we'll go up. The climbing hooks are attached at the top of the first stage. We didn't attach them to the final stage because we didn't need to climb that high, but we could have if we wanted to. Rev extrusion is very similar to 80/20 in that only a single nut holds the roller onto the extrusion. We found that in high-load applications, the nut can rip through the extrusion. We recommend that once you find the correct location for your roller, you drill through the entire extrusion to make sure that the nut doesn't rip out.
Hey guys, I found it!
At the end of the match, our robot has to stay attached to the tower. So our hook is right here, and it's attached to the first stage of the telescoping lift. It's possible that our robot will have to support the entire weight of another robot. So given that, we have to have a secure mechanism for locking the lift. This occurs via this small 4-bar linkage powered by a servo. So the servo rotates, and this C goes over the first stage of the lift, preventing it from falling. So this will hopefully keep our robot locked onto the bar.
One of our special features that we decided to implement was to implement a system to where people can hang off of us. Since the 13 inches that we have to hang at the end of the game is really difficult to hang with multiple robots. So we developed this. What it is a 13-inch wide bar that's designed to mimic the bar found at the end of the game, except on our robot. So it really doesn't matter. Other teams don't have to conform to our strategy. They would just have to climb like they would be normally climbing, except they'd be climbing on our robot. So the way we do this is we stays like this in a normal configuration through the majority of the match. And at the end of the match, we have this little tiny servo. The servo spins, it deploys, and then people can grab a hold of this. And we have tested it, and it seems to be holding, and we do use a bungee cord here, surgical tubing, to act as a spring to keep it down. So we decided on these dimensions for one major reason. That's because this robot's long enough to where any robot hanging on it will actually be compared to the ground instead of the platform, which is 3.5 inches taller than the ground. This is super cool because this allows us to put this 3.5 inches below what the normal tube would be when we would be climbing. A few other considerations we had instead of this were to actually put this on the side, so there would be two robots climbing on either side of you. This is a little bit more difficult simply because if one robot fails, both robots will fail because there will be an unequal balance in the system, and it'll be hard for anybody to hang.
So two possible climbing strategies that we thought about but didn't decide to pursue for one reason or another were one, to actually build a ramp bot, kind of like 2007. And so how the rules are defined, you need to be contacting the scale either directly or transitively and be above the bricks to count for scaling. So you could have ramps that raise two of your partners up above the bricks, and both of them would get the points for scaling, and then you could get the points for it through the levitate power-up, and that would get you that ranking point. However, we found this, we thought that this would be extremely difficult. So to just have passive ramps that they would drive up to that height would be incredibly steep and unfeasible, and actually lifting two of your partners up that height is another thing that we thought would be super difficult to do, especially in only 3 days. So for those reasons we decided not to pursue this. The other idea that we had, instead of trying to mimic the bar like we did here, would be to climb up and then lower down a rope for your opponents to climb. We think that this would be an easy thing to do because a lot of teams may have actually prototyped how to do this for one reason or another. And so if there was a large enough consensus and people kind of had ideas on how to do this laying around for some reason, that could be a cool way to get two robots on the rung relatively easily.
Stay tuned for a review video.
Make sure to follow our social media and our build blog to stay tuned to any updates.